Okay, while we're setting up, our final speaker is going to be Mr. Jihoon Kim. I believe he was introduced yesterday, but I'll reintroduce him again. He's a senior statistician in the Division of Biomedical Informatics. He has extensive experience in supporting investigators, as you just heard, in various statistical matters, including design of experiments, sample size calculations, implementation of software to support statistical analyses, and reporting results in scientific publications. He's going to be talking about a tool that he developed called, is it MAGI or MAGI? MAGI. And it's available through the iDASH website, and he's also going to be doing a demo.
So I'm going to do some introduction on MAGI, a web service tool we used for DBP1, the Kawasaki microRNA sequencing. Also, I will focus on the big data part. So MAGI stands for microRNA analysis in GPU infrastructure. There were many different names. This is the final one, hopefully. So this is the first front-end screenshot. It's we focused on. So when we talk about software as a service, I only focus on software, not the service part. So that's why the big data part, which is the core part of this talk. So web service. People love web service in bioinformatics area because it provides computations and users submitted data via web service. You don't need anything, you just need a browser only. So maybe you need to log in, maybe not, and you upload and you fill the form just as you get a credit score after you're fulfilling your address, SSN, birth date, and name and other things. And all the credit check or payment history or amount owed, these are not easy things because you have to look into different financial institutions, but that's all done by behind the scene at the back-end engine. So as a service, it's a user we don't need to know about. I don't want to know about as long as I get some credit score. So we want to have bring that kind of service to the biomedical users, like where you can upload your data and forget about it, you get the results. So one good example is Inspect that Claudia has mentioned for mass spec data analysis. So let me start with a little bit about microRNA. It's a non-protein coding RNA with an average size of 22 nucleotide. So nucleotide or 22 characters in computer science terms. It's one of the regulators that target protein coding genes. So with the advent of next-gen sequencing data accelerate the discovery of new microRNAs. So discovery of KD, so our assumption was that we could use the microRNA as a biomarker for diagnosis of KD. So our previous web service I had presented last year was about, as in any other web service, there's a front end on the web browser and a back end computing, which users don't want to know, and there's a final output on the web report. So our input was microRNA sequencing data, and the back end computing, two things: linking other databases, as in my analogy with a financial institution. Also, there's some prediction testing compute engine, either statistical testing or prediction. And then finally, a user wants to get output so they can publish right away. But there were frustrated users. We thought our tool was great, but users did not upload their data to it, period. So, but it's not just our tool, because the users did not like the idea of running pre-processing scripts in their local machine, which is common in web service for microRNA sequencing data analysis. And last year, we had provided a Perl or Python what we call downsizer tool, so that user, since data is too big to upload via browser, we asked the user to download the script and run it, but they usually talked about the primary reason they come up with is the security, but usually I don't want to, or I have no, I'm scared of Python, whatever, the Perl. I don't like the touching the computer other than browser was the typical response. So sequencing data was just too big to get uploaded to via browser. So this is a ubiquitous problem with any web services. It's not just ours, because when it comes to short-read sequencing data. So Nucleic Acid Research is a mid-high profile journal because they recognized that there's a value of a web server. So for more than 11 years, they had collected annual web server issue designed for allow the web server only, no login, upload data. So this was very popular among bioinformaticians. But as of last year, they changed their policy. Even though they still call it NAR, and on your right hand side there is their logo web server issue. They start to allow command line tool because of this huge sequencing data, the size of sequencing data. So limitation, big issue. So many people talk about big data. So what is definition of big? So our definition, here's our definition. Data is big if a user cannot upload it to the web server through a browser. So in that sense, the 2 GB is our data, the size of definition of big, because that's the practical maximum size of data transfer due to limitations coming from browser, web server configuration, or any network condition. Here, don't think about downloading your movie or drama in your home. Here, I'm talking about uploading data, which is way more difficult than downloading. So the size of small RNA-seq data in our KD data is about 1 to 3 GB per patient. So in our case, we have 12 acute convalescent, making 24 total sample size, which make total size of data is 23 GB. So previous solutions, what others did overcome this data transfer issue via browser. So sequential upload, you just upload 24 times. So this is tedious, laborious, sometimes you get lost. So there's also general purpose compression. So we already saw a lot of compression algorithm. But even after compression, data is still big. Compressed KD data size is about 7 GB, still too big to send over via browser. There's also pre-processing. This was our approach last year. But user has to still download, install, figure out the parameters to run the downsizer script like Perl. And also this is a platform dependent. And there's also additional tools approach like a plugin. But again, it's too much hassle and not secure. That was the typical response from the user. So let me briefly explain about evolution of JavaScript, because that was our solution, choice of solution. Before server-side, there was no such thing as server-side JavaScript. This was unthinkable a few years ago, because JavaScript was criticized for poor runtime performance, limited memory management, lack of ability to be easily integrated into the operating system. But now, with Google did a great job on V8. That's why they, you might have seen the commercial why the Google Chrome is so fast, because they rewrote whole thing written in C++ and fixed all above problems. So our solution is using software platform called Node.js. This is a platform that used to build scalable network applications. It utilizes JavaScript, scripting languages, and achieves high throughput using terminology called non-blocking I/O and a single-threaded event loop. I wouldn't go much in detail, but let me just go over, show you our MAGI architecture. Here, I focus on the data transfer part. This is a split into client on your left, server on your right. It's a simple 1, 2, 3 steps. Step 1, upload raw data into the through web browser. And then server, and number 2, that's what's happening behind the scene. We use Node, which is on top of JavaScript, and also the V8, which is a Google Chrome engine, and also we use a SQLite database. And also for expedited computing, we use GPU. I think we presented this last year. And there's additional statistical test and prediction analytics engine on top of it. But that's all done behind the scene, and then the user gets email, because typically our KD24 dataset took about 3 hours to run, and because a browser cannot send that long, but you lose connection, so user get an email notice that it is already ready. So what user has to do is just click URL to discover report, and he or she publish the paper the next day. That's our goal. So compared to the 2012 last year version, I added the first 2 rows. Added this here as a fast queue, the real row, which is directified coming out from the sequencing machine as input. So this is only MAGI handles this, but there's another tool called Mirror Express, which is not a web tool. And there's a read quality report, because of data size, people had to ignore which is about half size of data. They had to just cut off the quality, didn't do anything about it. But we handled the quality, because I have a statistical background. The quality I think is important. So web service, this is comparison report, DSAP, Mirror Analyzer, Mirror Express. So these are, MAGI only achieves all the comprehensive features, as you can see. So test run with real data. So again, we use 24-hour FastQ files, and total size again about 42 GB. And if you pick up one FastQ, one patient file, number of short reads about 15 million. So output is about 24 read count, what we call read count file, because we just hash it into finally this is expression data, not the genome data. So goal is to measure expression, and then we do the differential expression. So total size is a 51 mega. So it's from 41,000 mega down to 41. So we didn't intend to do the compression, but indirectly, in a way, we did a compression. The compression rate is about 400 times. I had to divide by 2 because I think it's not fair to include the quality score. But there's some this is not accurate number because I have to do some headers and other things. But still, it's greater than 100 times compression yield. So transfer time is about 48 minutes, which is about 2 minutes per FASTQ file. This for the interesting thing is we leverages the client computing power. So I measured this using Amazon EC2 data center, which is located in Washington D.C., right next to about 10 minutes near Washington Dulles International Airport. So this is a DC to San Diego time. So if you don't find a big difference between local because mostly our data file is so small that that transfer time is kind of negligible because we don't just do the compression but also the pre-processing in advance. So and here's the demo part. So this is a website. The user comes in and type in the email, and then for any run, run ID because typically people run many run. And here's a primer because Biochem 101 because enzyme cannot initiate but extend. So you just upload file. Here's a browser. You just selected all raw FASTQ files. You just drag and drop into the browser, and then you start to process each file. So I really wanted to show the whole 2 minutes because just brag about how fast it is, but I was told to do something like cooking show, so I'm skipping all because it takes like 15 minutes. So in the backend, we use for the technology savvy people, we use both JavaScript, Node.js engine, and also WebSocket to send the file. And then once the file is uploaded, then you start to, we recommend users to bookmark the whole, because on the URL, you see that there's hash ID, which is a unique identifier. Of course, we will send this to the email back to you, but in case you didn't put email, because when Dr. Burns submitted some data, everybody knows it's a Kawasaki data. So some people are reluctant to input their own email. So that's why we put, so this is the, from the email, Outlook email, you got a URL to discovery report, and this is the quality report. Because you see a lot of up and downs, but Illumina new HiSec 2000 is very reliable. All of most of them passed the quality. This is histogram, and this is a genome mapped read. The dark blue from how many reads are mapped, both counts and percentage, and in the JavaScript. And among the genome mapped, we also mapped to RNA because even though this protocol was intended to measure expression of small RNA, but they also measure some other RNA, such as like small nuclear RNA, tRNA, RNA. So because this is like noise when you want to do the small RNA analysis. And if you pick up the null marker RNA, you see the secondary structure, and this is a read count on your bottom. So the green one is a reference genome, and the read count is mapped into that. And that was known, and this is novel part. So these are predicted microRNA, and this is new target microRNA to gene relation, the prediction results. Yeah, and that's all. And this is teamwork. I'd like to thank all of the people described here. Thank you. I'll take some questions or comments.